Alright, it's about time to start the stream. Hopefully everybody can hear me. For anyone who hasn't seen it before, in this stream I am broadcasting the creation of my math videos, which you can find on YouTube as Math for Game Developers. And they are an explanation of the math that's required for video game development. From the ground up, assuming no college level math. So at this point we are talking about fixed point iteration, and we are going to do a video. Actually, let's see, how many people are in the stream at the moment? A few people. It's actually going to present a choice. That being, do we want to do this? We can do this. We can talk about fixed point iteration, which is very cool and useful in not just numerical analysis, but also in a few other things. Or we can talk about another project that I've been meaning to get started on, sort of a secret project, that has to do with like a complete redesign and replacing of my videos with interactive web pages. In the end, it would be kind of similar to my videos, but and you know what? I'll show for the 3 people who are here and can vote at the moment. I will bring it up. No, it's just here we go. No, that wasn't it. So I did a talk in, this uses OpenGL pretty heavily, and hopefully that doesn't cause any problems here with the streaming. It's crawling, the frame rate is crawling for me, so, but you guys can just load up this URL and see what I'm talking about. So this was a talk that I gave in November, explaining what is a vector from a visual standpoint. And so this is a vector, and it's an interactive web page that people could load up and mess around with during my talk. And the subject matter covered is the same as the subject, and you know, it talks about what is a vector, coordinates, how to add 2 vectors together, and now it's frozen. There we go. So this is the same picture that I drew early on in my videos of vector addition right here. And the idea is to have something like this, something like that I did in the talk, but have it play more like a video, but then at the same time be interactive, like an interactive video basically. With this web page as kind of a starting point for developing my ideas there. So thank you, Jan. So I want to develop this into like its own web page that would talk about linear algebra, which is what this is, from a more general perspective, not just making video games, but using video games as examples, as motivations, because I believe that people understand mathematics better when it's motivated, when there are applications. So we can work on that, or we can work on fixed point iteration, and I figured I would leave it up to the channel to decide, all of the 3 people who are currently watching. So if you have any thoughts on that, then send me a message, and I'm up to do whatever. We can talk about this for a little while and then go into that. But I thought it'd be interesting to give you guys a view into what I'm doing. I don't know, a choice, and see what do you want me to do. The website is in JavaScript, so if you guys want to see some JavaScript coding, we can do that. I'm not terribly good with JavaScript, so that might be fun. Well, in the meantime, let's start thinking about fixed point iteration here. Yeah. So that's the thing. We won't actually be getting into any interactive demos of fixed point or any like numerical analysis. This would, like, if we work on interactive video project, then that's really just like drawing and coding and really not learning that much math. I doubt I'll actually finish anything in this session. So if you want to learn math, you know, pick learn math. If you want to watch coding, pick watch coding. I don't think we'll have really time to do both. Once I get some work in on the system, then it will be, you know, then we can actually learn some math. Although, again, not anything that we didn't already learn at the beginning. This is for the benefit of the internet as a whole. I want to create something new that's not ever been done before. And that could be cool, but we're not going to learn anything doing it. Let me draw a picture of fixed point iteration. Oh, don't need that anymore. I'm at the disadvantage where we're waiting for the delay to catch up with our wonderful viewers. No. There we go. Yeah, I think you're right. Let's do some fixed point. I can code later. So we have a graph. Or we don't. All right. We have a graph. See how straight I can draw a graph. Photoshop had this thing where you could force it to draw a straight line, and I'm still trying to find out what that is in Mischief. It may not exist. That's fine. I'll do my best. That's mostly straight. So here we have a curve. That's a bad curve. Well, it's an okay curve, but I can do a different curve. This is f of x. And someone's calling me. I don't even know who that is. So here is also the line y equals x, or f of x equals x. And these 2 points intersect. Bam, right there. And that is called a fixed point. The fixed point The fixed point is the point at which f of x, some random function f of x, equals x, right there. That's where the function, you know, I'll call this, I'm going to erase this. I don't want any confusion. There's only one f of x. It's this red line. So this point right here is the point where the function f of x is equal to x. So if I put x into the function, the value of the function at that point will be x. That's a fixed point. So let's see, how's this useful? See what the book says. I can't think of any applications offhand. Well, there's an obvious application, but I don't want to get to that yet. The book doesn't cover any applications. That makes me sad. Let's look on the internet. Fixed point iteration. Okay, none of this is useful, so I'll just go to what I was going to explain. We're talking about root finding problems, and this is not a root finding problem because we're not finding a root, we're finding a fixed point. So WTF, mate. But you can transfer any fixed point problem into a root finding problem. Let's do that. Okay, this was f of x right here. Now I'm going to draw a new curve, f of x minus x. And it looks something like this. This is f of x minus x. And we can see the point where f of x minus x equals 0 is the same as the point where f of x equals x. You just subtract x from both sides, right? So now we've found a, now we've made a root finding problem out of this fixed point problem. If you call g, let's say g of x equals f of x minus x, then root finding for g is the same thing as fixed point iteration for f. So let's do it the other way. Let's say that this is some random function g of x, and we want to make it into a fixed point. So this is a root finding problem right here. We're going to find the roots of g, and let's say we want to transform it into a fixed point iteration problem. Well, then I'm going to make this h of x, well, let's do it this way. Might be more clear this way. G of x plus x equals x. So if I make h of x equal to g of x plus x, then I can do fixed point iteration on h, and that will be the same as doing root finding on g. So fixed point iteration and root finding are really the same thing. They're like isomorphic, to use a kind of a mathy term. So if we can learn how to solve fixed point problems, that might make it easier for us to solve some root finding problems. So let's see what the book says on solving fixed point problems. And where's the theorem? Here we go. Here's a great picture. So it turns out if you have a special condition satisfied, that condition being that it is a contraction mapping, your function is a contraction mapping, and I'll explain what that means in a moment, then in order to find the fixed point, all you have to do is keep pumping that number through itself over and over and over and over. So you have P right here. P is your initial estimate. Where is it down here? Here's P naught, P1. So P is like P naught. P naught is your original estimate. You use it as an input for your function and you get P naught. I'm sorry, you get P1. And then you put P1 into G and you get P2. Then you put P2 into G and you get P3, and so on and so on. And eventually you close in on the fixed point. Let's maybe load up an example of this. LDB. Can we do this? Print cosine x. No, wait. Print cosine 1. No, it won't let us do it in LDB. Let's try Python. Print cosine 1. Math.cosine 1. Import math. I'm just stabbing in the dark here. Math.cosine 1. Yeah, there we go. Haha. Okay. So, going to the grapher that we used last time, which was really cool. Let's look at cosine of x. There it is. And now let's add another one. Add another equation. So we're looking for this point right here. What is the point at which cosine of x equals x? So that's the intersection of cosine of x and x. What is the value of x at that point? Oh, we have a pretty good approximation for it right here, actually. 0.7524. And the way we're going to do that is by using 1 as an initial estimate. Where was it? And taking cosine of 1 is 0.54. Now let's do it again. Math.cosine of the result of that, right? So that's going to take the cosine of 1 and feed it back into cosine, and you get 0.85755. So that's, let's see, what was our estimate? 0.7524 minus 0.7524. The original estimate, this is going to be our first estimate, it was 0.212 off from the actual. Now let's do this one, minus 0.7524. You can see this one's a little closer. Now we're 0.1 away from the actual. And let's do it again. Math.cos. Our new estimate is 0.654. Let's see how far away that is. 0.75. That's only 0.098. So you see we're drilling in and in and in to what the actual value is. I'm going to do one. I'm going to do two more. Math.cos, math.cos. Why not? Three more. Math.cos. And close all those parentheses. So now we're at 0.63. What? I can't even read. 0.763959. And let's see what this gives. So if I put this number into math.cos, since I found a fixed point, I should get the same thing back. It's pretty close. It's pretty close. And the more I continue doing this, the better estimate I'm going to get. So I found that a solution for cosine of x equals x might be x is about equal to 0.764. 0.764. And that's not perfect, of course. I have to continue to iterate in order to get a more accurate solution. But it gets better and better as time goes by. Now, what root finding problem did I just solve? Cosine x minus x equals 0 is the root finding problem that I just solved, right? So then I'll have 0.764. Wait, no. I want cosine of that. So if I take cosine of that, I get what I had over here. It was 0.722. 0.722. That's if I just take this x and put it in here, that I get 0.722. Minus the original 0.764. And the difference between, so that's I mean, you can see that's about equal to 0. So we've more or less found the root. We need to do a little bit more of the iteration on our algorithm to get better accuracy, but we found the root, you know, plus or minus 0.04 of the function cosine x minus x. And let's graph that function so we can see what it looks like. New equation, cosine of x minus x is, there it is right there. So what did we do? What function did we do root finding for yesterday? Maybe we can make that into a fixed point function. Yesterday, last week. Oh, that's right. We found sine of pi equals 0. Sine of pi equals 0. Well, that doesn't really break down into a fixed point function very well, so that's a bad example. Honestly, though, sometimes you really just want to find the fixed point of something. It's like the stable point. And I'm kind of disappointed that I can't think of a good video game example offhand. Because I want to say I've even used this before. Let me look in some old source code. I am positive that I have used fixed point iteration before, and I think I know the answer of where it was. So my repository is this one. I think it was for the physics simulation in this blue ocean thing that I showed last time. So what was that? The Seaweed? It was the Seaweed. But that's only an H file. Oh, this was it. Okay. Seaweed. Yeah, this is to initialize everything. Simulate Seaweed, of course. Simulate Seaweed. Actually, let me just play the video once more so that we can see what I'm talking about. And for this Seaweed on the side here that moves out of the way once the camera comes through. So that's like real-time physically simulated right there. And also when the big blue thing shows up, it does this backing up more. Here we go. So it starts to pulse in and out, and then it does this it gets really, it does this thing where it shoves everything out and then it shoves everything back in, and you can see the seaweed all reacting to that. These stalks of seaweed, they're all physically simulated and they kind of react to that. They react to the pulse. So I think in the physics of that simulation is when I made use of fixed point iterations. So let's see. Oh, simulate seaweed is not in this file. Lame. Where is it then? Simulate seaweed. Here it is. It's in a header file for some reason. Okay, now I have to stare at this for a few moments to figure out where was the simulation that I'm interested in. Where was the fixed point iteration? Oh, this was a Newton, not a fixed point. This is a really cool trick with Newton, but it's not fixed point, it's Newton. So let's see, what was that? What was that formula? 2 times length squared over dot product 2 times length squared over the s dot s minus the length. What is section? New position minus lower link position. Yeah, yeah. So we have a section of Seaweed, S. This is a vector S. And then it has a length, like the length of S is L. Or wait, the length of S is L? S is L? Length squared. What is that? Oh, that's the... Oh yeah, this algorithm's really cool. Yeah. Okay. So that's not this. L is the desired length of the Seaweed. Okay. So maybe the Seaweed is this long, but this length, slightly longer, is L. And L is like the ideal length. Like if the Seaweed gets compressed a little bit because of some physics simulation, then it just wants to be the length L. And when you use this function right here, this little bit of math, did I copy it down correctly? I missed a square. It does a fixed point iteration on the length, and I can explain that later. It's kind of tricky, actually. Do you even remember how this is? Why this works? I don't. But it does a fixed point iteration on the length of the section of Seaweed. And you run it once every frame, and so it just kind of tries to find the right length. This does seem like a problem that could be turned from Newton into fixed point pretty easily. Why is it Newton? So we have the length of section right here. This is the current length of the section of Seaweed that we're simulating. We put it here. We get this R. R is like a scalar for how long it should be. It's not a Newton. This is a fixed point. Why did I call it a Newton? It's totally a fixed point. Lower link position, that's this. That's that part right there. So you're taking the lower link position and scaling the length of the link by R, which you want to normalize at length squared. Because if section, okay, yeah. So suppose that when you do this s dot s, since okay, we remember the definition of cosine. That's a dot b. These are both vectors. Is length of a times length of b times the cosine of the angle between the two. And so if it's s dot s, then this is just length of s times length of s times cosine of the angle between s and s, which is 0, and cosine of 0 is 1. So this is times 1. So this term just goes away. This factor just goes away. So this is really just length of s squared. So let's write that. 2l squared over length of s squared minus l squared. Should that be plus l squared? Yeah, it is plus l squared. Plus. So let's say that s, the length of s is L. Suppose length of s is L. Then length of s is L, I'm just going to do substitution. 2l squared over L squared plus L squared that just cancels out. That's equal to 1, right? So when this function, think of this as a function, the length of s, when it's equal to itself, that sounds like fixed point iteration to me. And if you run this formula a bunch of times, then that's what you get. That's what you get. Is it settles on the length that you like ideally want it to be. I hope all that made sense. So yeah, this is a pretty good example of fixed point iteration. And unlike what we did last time, unlike the what was it that we did last time? The cycloids, the water, like we saw this GLSL code that was too optimized to any longer actually resemble the what did we do last week? Oh my god. Oh yeah, bisection. It no longer looked anything like bisection method. But this actually does look like the formula that we're using, that we want to use. So that's not really a Newton. That's a fixed point iteration. But that's fine. I think there's a perfect example for us to use, and it'll make for a really good video. Just the comment is wrong. So that's fine. And I think actually, like, so if you have, you know how in some new games there are simulations for plants and stuff, where if the player goes next to the plant, then the plant moves out of the way, like it kind of brushes the plant aside. Those plants are modeled like sections of springs like this, okay? Like this is a plant where each section has a length, okay? And each section has like an ideal length that it should be. If you pull it a little longer, then it just wants to snap back to its length. And if you pull it shorter, it snaps back to its length. And then it also has like an ideal orientation that it wants to be. And if you pull it out of the way, then it'll just kind of flop back to where I want it to be. Like if you pull it over here, then it'll go boo, 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 with my killer sound effects. That's how they model these plants. They're just simple springs, and they look really nice. And it's possible that a lot of them use something like this. I know that some video games have used something like this, where they just do, instead of doing all of the fixed point iteration steps every frame to lock it in place, they use this trick. They just do one fixed point iteration step every frame. And because the first step in the iteration, you cover the most ground, it gives you this spring effect where like it moves fast and then it starts moving slow as you like narrow into the equilibrium point. So this is cool. Let's, just for completeness here, let's take this through the entire process. This is R. And what we do is, okay, let's give this guy a name. He's X0. That's S. So what we do is we want to find the new like endpoint for the top of the seaweed. And normally that would be X0 plus S is the endpoint before we do this iteration. But then we're going to scale it by R. And let's see why that works. Let's say S is a little bit longer than the ideal length L. Okay? So S, do that down here. Absolute value of S is longer than L. Okay? That means 2L squared over absolute value of S squared plus L squared. So that means that this denominator right here, with absolute value of s squared plus l squared, will be strictly greater than l squared plus l squared, because s is bigger than l. So this denominator will be bigger. That means the whole thing will be slightly less than 2l squared over less than 1. Yeah, so a bigger s makes us less than 1. And so that means, so this is r, so r will be less than 1, so the new endpoint will be a little bit shorter than it was before. And if we do the same thing where length of s is less than l, then we have r is 2l squared over length of s squared plus l squared. And here we have that s squared plus l squared is less than l squared plus l squared, because I'm just applying this. And so the denominator here is going to be smaller, and so that makes the entire thing a little bit bigger than 1. And so that will be s times something bigger than 1, and so we're going to get slightly longer in the next frame. So how would I draw that on a graph so that we can see it's a fixed point iteration if we want to see that? It's a pretty good graph, actually. I think I need to put r here and length of s here. Yeah, and then I'll graph it like this. Let's turn these off for a moment. Well, we'll keep that one. Let me make a new equation. I've never thought about this quite in this way, so I'm kind of learning something new here too. Let's use 2. See, I can't just use L because I haven't defined L. So I'm just going to assume L equals 1 for now. X squared plus 1. So that is 2L squared. If L is 1, then that is 2 times 1 squared, which is 2. In the denominator, I have x squared plus L squared. L is 1, so it's x squared plus 1. So that gives us this. Oh, that's an interesting curve. That is a very interesting curve, and we see it has a fixed point right here at 1, 1. Now I'm going to do it again, new equation, but I'm going to do it with L equals 0.5. So that is 2 times 0.5 squared over, let's get a bigger over, x squared plus 0.5 squared. 0.5 squared. All right. So the ideal should be, this doesn't look right because we want this thing to be 1. Oh, yeah. Okay. So when x is 0.5, the value of this thing is 1. And that's what we want. But now I realize it's not quite fixed point iteration, is it? Now I've made it into root finding by subtraction, because what we want is to find out where it equals 1, not where it equals itself. So that means it's not quite a root finding problem, or yeah, it's not a root finding problem because you're not trying to figure out where it equals 0, and it's not a fixed point problem because you're not trying to find out where it equals itself. You're trying to find out where it equals 1. We can turn it into a fixed point problem by adding x like I did before. So now when you, and again, I'm not doing anything crazy here. We added x to turn a root finding problem into a fixed point problem. So that's why I added x right here. So now it is a fixed point problem. Let me do one more equation here so I can see all the pretty. So let's see. 2 times 2 squared over x squared plus 2 squared. 2 squared. And then minus 1 plus x. Well, let's say plus x minus 1. So now when I put 2 into there, I will get a 2 out. That is a fixed point problem. And we can see we have a nice family of curves here that kind of resemble, I don't know, these little swooshes. They look pretty. I like curves. Curves are pretty. So okay, this isn't quite a fixed point problem. Can I work around that and present it as a fixed point problem? Because we are doing the exact process of fixed point iteration. Because, I mean, you can see when we multiply s times r, we get a new s. So like s prime equals s times r. And it's the new length of the thing. So the thing has a new length and it is, and then we use it as the input of, when we do the next time. So like in the next iteration, the s is going to be what the s prime was last time. So it's really, if it's not exactly fixed point iteration, it's really similar. It's the same process. And it's not something I would feel bad as representing as fixed point iteration, especially since it's a really cool algorithm. So let's see here. Maybe I could write it like this. Let's erase this. S, so let's see, Sn plus 1 is equal to Sn, these are vectors, times 2L squared over length of Sn squared plus L squared. So now S is my input vector. And we are looking for when S this is like a function that takes S. So this still does what it, so this equalizes when S equals L. This stabilizes. when the length of S is L, which is still not quite what I want. Turn that guy back on. Yeah, let's do this thing. Let's just write this here and see where it goes. Plus, what was it? Plus length of S n minus 1. All right. Now it stabilizes. So if I put a vector of now I have to think about this. Plus x minus 1. When the length of S is L, this part is 1. So let's say length of S is L. Then that means this part is 1. And so we'll get Sn 1 plus length of Sn minus 1. The 1's cancel out. And so that equals Sn. So that is a fixed point. That is a fixed point. That is what we want. If Sn is bigger than L, then this part will be a little smaller than 1. Let's do that. S is bigger than L, then we're going to have S times something a little bit smaller than 1. Smaller than 1 plus Sn minus 1. So that will be a negative value here. Length of S. So something smaller than 1 minus 1 is something a little bit less than 0. Or, you know, somewhat less than 0. And so we're making this vector smaller. Making it a lot smaller. No, I definitely screwed up here somewhere. No, this is fine. It's like it's just like subtracting a little bit from it. So we get something like S. Okay, yeah. Something a little bit less than 1 minus 1. It just subtracts a little bit from the length of S. And you get something. So this right here is, you know, less than the length of this thing is less than the length of S. So when S is too big, S contracts. And then the result is the opposite is going to be the other way around. When the length of S is bigger than L, it will expand. That makes a little bit more sense to me now. Let's go back to the code now. So the parameter L of this function is it's just determining where the fixed point in this family of functions will be. Where's the family of functions? Here is the family of functions, and the fixed point is at x equals L. It's getting hot in here. So let's see here. Yeah, when L is 0.5, you get this one, and the fixed point is at 0.5. When L is 1, you get this one, the fixed point is at 1. When L is 2, you get this one, the fixed point is at 2. So that works fine. So I've modified this this weird formula that I had to be a fixed point formula that we can use fixed point iteration on in order to do a physics simulation. That's totally game application, and I can use it to make a video. So let me erase all this stuff. And I'm going to go into a new folder. What is our new name? Fixed point iteration. And erase all this stuff. We are no longer doing floating point numbers. We are now doing clear canvas. We are now doing fixed point iteration. And of course I just erased my formula. I'll write it here in the sidelines. I don't think this will be in the video. I think the edges will be here, so I'll just be able to use it as a cheat sheet. I do this way too often. So it's parameterized by L, and then we have 2L squared over length of S squared plus L squared plus length of S minus 1. And this is a vector valued function. So I need S times this. How do I present this though? Okay, so I know the formula now that I want to present. Even though I had to struggle through much confusion in order to find it, but I found it now. The question is like how to present it. Like, do I want to just write it down without deriving it? Oh, and I never explained what a contraction mapping is. Oh, that's important. So what are the limitations of using fixed point iterations? There's only one. You have to have a contraction mapping. What is a contraction mapping? Maybe I can give an example of something that's not a contraction mapping. Okay. So let's say this is A and this is B. And here's also A and B. Okay. And we have a function that takes AB to real numbers. That is that my function is defined on this interval a to b, and for every point on this interval a to b, the function will give me some real number. That's all this notation means. But the problem is the value of the function at a is less than a, and the value of the function at b is greater than b. Okay, so is less than a, and then here's my function. That's not a contraction mapping, because the range of the function, here's the range, is larger than the input range. So that, like, the range of the output is larger than the range of the input. The input goes from a to b, but the function goes from something less than a to something bigger than b. So it expands, right? It's an expansion mapping. Now let's do the other situation, the contraction mapping situation. I'll make a function g that takes this interval a, b to any real number. But for the contraction mapping, I'm going to say that g of a is bigger than a. Does it have to be less than b? We'll get back to that. And g of b is less than b. And here's my function. This is a contraction mapping. So you can see g squeezes my input range, ab, to a smaller output range. If it doesn't do that, then so where's my fixed point? Right here. If it doesn't do that, then I won't stabilize around the fixed point. Here are my fixed points. And I can, let's see, can I give you an example? Yeah, I can give you an example of where that will actually, maybe the textbook has an example. Let's look at the textbook real quick. Right. So I think that this function x squared minus 1 over 3 is not a contraction mapping. Let me read here real quick. Reading math textbooks. Yeah. So for this range from 0 to 1, g of 0 why is it talking about natural log of 3? Oh, this is the function 3 to the negative x. Okay, let's take a look at what 3 to the negative x looks like. 3 to the negative x. There it is. That is a contraction mapping. That's totally a contraction mapping. Because from 0 to, in the range from 0 to 1, the output goes from about right here, which is 0.33, to 1. So 0.33 to 1 is less than 0 to 1, is a smaller range. So that should be okay. What's going on here? Does not ensure a unique fixed point on that interval, even though oh, that's because I'm looking at the wrong thing. What is theorem 2.3? Theorem 2.3. Oh, that's not what I want. I don't even care about that. All right, I just got to find a function that's not a contraction mapping. So I'll just make one up. That's fine. The textbook doesn't have an example. I don't need one. I can make one up. Actually, I think the text point did have one, but it just didn't talk about it. What was this? what was this? X squared minus 2? Yes, this will work fine. X squared minus 2. Oh my god. X squared minus 2. All right. So where's our fixed point? At 2. Fixed point is at 2. What is the value of this function at 1? It's negative 1. What is the, it's negative 1. This function. It's negative 1. What is the value at 3? It won't let me do it. But let's see. 3 squared minus 2, that's 9, that's 7. It's 7. So 7 is way bigger than 3. I'll write this down over here. So x squared minus 2. Let's say our function is f of x is x squared minus 2. And our interval is 1 to 3. So we've bracketed our fixed point. And this goes to real numbers. So what we want is that f of 1, let me do this. F of 1 is between 1 and 3, and f of 3 is between 1 and 3. That's the requirement for a contraction mapping. Oh, it also has to be continuous, but we assume that for all of the functions that we're talking about, that if they're not continuous, then we're not doing numerical analysis on them. But that's not the case, because f of 1 is equal to 1 squared minus 2, which is negative 1. And f of 3 is 3 squared minus 2, which is 7. And so neither of these fit the definition of contraction mapping. Instead of contracting, they expand. So now let's go to the Python shell and see whether this gives us a fixed point. What was it? A fixed point around 2. So I'm going to use 1.5 as an estimate. Okay. Actually, can I just? How do I define a function in Python? I have some Python code. This will help me. I'm gonna figure out how to define a function in Python real quick, and that will help me. Yes. Function. There are no functions in this code. Of course not. That doesn't help at all. Okay. Google Python function. I know Python, but I'm not familiar enough with it that I have all of the syntaxes in my head. So every time I write Python, I have to basically go Google all of it. There it is, def. Okay. So def function name parameter. I remember now. Okay. So def, I'm going to make a function called x that takes a value and it returns x times x minus 2. So that is x squared minus 2. And I forgot to indent it, so let's try again. Def f of x return, this time I actually indent it because Python likes that. Do I have to say end? No, I don't. I'm done. Okay. So now if I do f of 1.5, I get 0.25. So let me do this. So 2 should be a fixed point of this function. And it is. If I say f of 2, I get 2. That is the definition of a fixed point. F of x equals x. And f of 2 equals 2. But if I do f of 1.5, I get 0.25. So it's not converging to my fixed point. 0.25 is farther from 2 than 1.5 is. Of course, 1.5 is a distance of 1/2. 0.25 is a distance of 1.75 from 2. And let's try the other way. If I choose something slightly above the fixed point, then I get 4.25. So it pushes me away from my fixed point. And I think I can actually draw a pretty good graph of this. What visualization should I use? To show this? How do I draw this graph? How do I draw this graph? I'll do it like this. This graph will actually be good to have because after this we're getting into differential equations. And differential equations are very similar to what I'm about to draw. So let's say this is time. And this is like the value. Okay. So there are two types of functions, right? There are expansion mappings and contraction mappings. And let's say that this right here is the stable point, is the fixed point. All right. So if the value of x is this, then it's a fixed point. And as you do your iterations, you either get closer to the fixed point. You know, if your iteration starts here, then you get closer to the fixed point. I should use a different color for this. If you start your iterations here, then you get closer to the fixed point if you have a contraction mapping. If you start like if your initial estimate is there, then you get closer to the fixed point. So this is called stable. On the other hand, you can have something that's unstable. Whereas even if you start at a very good close estimate, if you have an expansion mapping, then it pushes you away from the fixed point. Every iteration you're going to get farther away, and that's an unstable point. So you have a stable fixed point and an unstable fixed point. This whole graph is called a phase plane. And we are going to study those more once we get into differential equations. So that makes me wonder, should I draw this graph as part of the video? Because we're eventually going to get into phase planes, and so it might be good to have kind of a little primer on phase planes and have something that looks like a phase plane right now so that it makes more sense when we get to it. I don't think so, though, because we're going to be looking at those phase planes a lot, and we should get plenty of practice with them later. So I'm not terribly inclined to cover them right now. I think this videos are going to be too long. All my videos are too long. So let's not deal with the phase plane right now. All right. So what are we looking at here? Oh, and I drew over the place where I wrote fixed point iteration really nice and pretty. Why did I do that? Now I have to rewrite it. It's just no big deal, but I am going to keep my beautiful formula, my cheat sheet over on the right there. Gonna keep that right there. Because there's no way I'm remembering that formula on my own. Ugh. look at how careful I'm being with good handwriting. When I know it's going to be recorded forever in the actual video, I do make an effort to have legible handwriting. Sometimes I just write like this and then no one can read it, but that's fine because I'm not recording it. So it doesn't matter. Okay. So let's try a dry run through here. And where's my timer? I can break the tablet out real quick. And try a timer. And do a quick run through of the video. This is weird since I think I have all of the stuff that I want to be in the video basically planned out, but I don't have any order or anything, so this still may not be a very good run, but we'll see. So we're doing fixed point iteration, which is not root finding. So first I have to explain what it is. Slightly different from root finding. We have a function like this, and here's y equals x, and here's the fixed point. So the definition of fixed point iteration is when you have this function g of x and it equals x. And why do we care about fixed point iteration when it is not root finding? The answer is because we can take any root finding problem and make it into a fixed point problem. And we can take any fixed point problem and make it into a root finding problem, vice versa. And here's how we do it. I'm going to define f of x, a new function, f of x, is g of x minus x. And when f of x equals 0, g of x is equal to x. So here is f of x, and you can see that it has a root at the same spot as our fixed point problem has a fixed point. Now, how do you take a fixed point, how do you take a root finding problem and turn it into a fixed point problem? Well, you just add that x back. And so I'm going to define that as a new function, h of x. And when h of x is equal to f of x plus x. So I define h of x as being equal to f of x plus x. And when h of x equals x, f of x equals 0. Yes, when h of x when h of x equals x, f of x equals 0. So we are interested in fixed point iteration, and well, what am I doing? I always start these videos with an example, and I didn't start this video with an example. I should start with that physics simulation example that we discussed before. So let's start again. Restart my timer. Reset. Start. So let's say that you have... Oh, this is going to be fun. I know it. You have a bit of seaweed. Off to a good start. You have a bit of seaweed like we have in our beautiful video. Physically simulated underwater seaweed. And each length of seaweed is individually physically simulated like this, and it has a few lengths on it, okay? And part of our simulation is that we want each length to have, each part of the seaweed to have an ideal length L, that it should always be that length L, okay? That's the ideal length. And we have the current, a vector that represents one length of seaweed. L is, let's use colons here. L is a vector representing a length of seaweed. A section of seaweed. I'll call it that, a section. And S just sits along the section. S is just a vector that sits along the section of seaweed. So what we want to do is figure out a physics simulation for this. Oh man, how do I explain this? A physics simulation for this chain of seaweed that tries to keep this length of seaweed at the same length. And we can use this to make nice, pretty, not just seaweed, but like plant simulations that we talked about earlier. Yeah, do I just jump out with this formula and just start writing down, and it's a huge formula, and then it like confuses people? That would be mean. That would be really mean. I could just do that. I could just say we have this formula, f of s, that gives you, that represents, I don't know, how do you even explain it? Like, it's a really cool formula and it does a lot of amazing things, but I don't know, I'd feel bad just writing this huge formula without at least trying to derive it. It's not so bad. I mean, I'm going to argue with myself on this a little bit. I mean, I can explain this part pretty easy. This part. I did before. But then explaining how we got the other part, this is just kind of derived, or what's the word? Like, we had to do a lot of mess to get this part. And it's not something that you just look at and say, oh, that makes perfect sense why there's a length of s minus 1 there. Totally. Length of s minus 1. Maybe I can change it to look like something different. I guess I should stop the timer, huh? Stop the timer. So what if it looks like this instead? 2l squared over length of s squared plus l squared. And then I say plus s minus plus s length of s minus s? Where does that get me? So I just distributed this s vector everywhere. But that doesn't really make any more sense than it did. Plus s times length of s minus 1. Nope. Yeah, there's nothing really that intuitive about this length of s minus 1 bit. Why it's there. What it can be used for. How did it get there? What is its purpose in life? None of these questions have straightforward answers. And I like to give straightforward answers. Guess I'm just gonna have to work around it though. So I can write this part first. This is the core part. We have 2l squared over s squared plus l squared. This is a trick. This is a little math trick to get a value that is 1 if if the length of s is equal to l. That is smaller if s is bigger than l, and is bigger if s is less than l. And then to turn it into a fixed point problem, we have to add these special values. So I can build the formula up like that. That's not too bad of a way to explain it. It's not my favorite thing ever, but it will work. Let's try that. Wait, but I can't say because that will turn it into a fixed point problem when I haven't defined what a fixed point problem is yet. That's cheating. Yeah, presentation of like deciding on the order of presentation is and finding an argument where each thing that I present connects to the next thing is probably the hardest part of making these videos. I don't know about the hardest part. Anyway, it can be really tough at times because you want people to, if people feel confused, sometimes, okay, I tutored math for a while, and sometimes people understand the thing, but they still feel confused. And so, like, that doesn't help. It's like, you did it, you understand it, but you feeling confused got you in the way of being confident about a thing that you actually know. And so I put a lot of effort into having a consistent argument that you can follow even if you don't really think about it very deeply. It may not be a very rigorous argument that's like any mathematician would go crazy over it, like a perfect rigorous argument, but at least makes sense to a layperson who doesn't care about a completely rigorous argument. And then that way they are, they feel like they understand the thing, and then when they want to go learn it, like actually go learn, you know, real deal, they have that confidence and you know, behind that understanding. So the order that I present things is really important, and I'm just not seeing a good order for this video. I feel like I have a really good example, a really good like thing that I can cover that is definitely a video game simulation problem, and that people who like to program video games might be interested in. And there's a really cool way of doing it, I think, a really neat formula. But how do I arrange my arguments in a way that won't like leave people going, why did he say that? So let's continue just so I don't beat this point into the ground. So we have this formula that will let us simulate the size of the length of the section of Seaweed. And the goal of this formula is that it should be stable. When S is the length that we want it to be, yeah, maybe that's how I can approach it. I can say, okay, this is the ideal length L, and if my section of Seaweed is shorter, we want a formula that gives us a longer length, a length that's a little bit longer and approaches the ideal length. And when a section of Seaweed is too long, we want a formula that shortens the length. So it doesn't have to give us a piece of seaweed at the exact length that we want. Oh, here's a question. Why don't we just use this formula? S times 1 over length of S, L. Okay, that will get us the exact, that will get us a new vector that is length of x, s, length of, sorry, a new vector that is in the direction of s, but is the length of L. And the answer, there are two answers to that. One is that this formula up here models a springy system better because it's not perfect. Like this will just slam the value to the length of L, and we kind of want some springiness to it. Springiness looks good. Two is that we can avoid this square root right here. This is like this length of S right here. If you watched my previous video, you'll probably know by now that it is the length of, it is the, what, like s dot x squared plus s dot y squared plus s dot z squared. And then you take the square root of that. And square root can be an expensive operation. So doing it this way, we get kind of a springiness, and we avoid the square root. Well, that's not true because we have this guy in here. Oh, we have this square root right here. Okay, what if I start with this? Here's what I'm doing. I'm going to start with this. I'm going to say this is a fixed point problem that we can solve, but if we change the format of it a little bit, then we can save on this square root. And now this is getting a little bit more complicated, but ugh. I feel like this should have been a simple video and I'm having way too much trouble with it. Let's look at the original formula again. S prime is S times 2L squared over length of S squared plus L squared. I think that was it. Yeah. So the difference is that this thing instead of, so the top formula has a stable point at f of s equals s. And the bottom one has a stable point at f of s equals length of L. So the top one is a fixed point, and the bottom one is what we actually want. Something strikes me wrong about that. Yeah, this is totally wrong. So let me walk through this again in my mind. So if the length of S is L, then this part becomes 1. And you have 1 minus 1 is 0. And this becomes which is like squared as long. So you have a length of S in here and you have a length of S right there. So it'll just get longer and longer. And that's not a fixed point at all. So I definitely screwed up somewhere. I guess today is not my best day. What do we actually want? We want a fixed point when the length of S is L. We want f of S equals S when S equals L. Okay, so let's take this out of here. This is a vector and this is a vector. So this part we can probably keep. Length of S squared plus L squared. When S equals L, this part is equal to 1. So just close parentheses. Why doesn't that work though? X is equal to 0.5 here. And the length stabilizes at 0.5. Oh, these formulae are wrong because of the extra s that I put in. Oh, I am so silly. I'm so silly. Okay. Let's go back here. I have to do like this. It is the extra x that was confusing me the whole time. Yeah, now it totally works. Oh, and it's an even prettier family of functions. Look how pretty they are. Okay. So for this guy, where's the smallest one? For this guy, when x is 0.5, the result is 0.5. So that's good. For this guy, when x is 1, then y is 1. That's good. For this guy, when x is 2, y is 2. That's good. Okay. So the fixed points are all exactly where they needed to be, and I needed to add an extra x because remember, x here represents the length of the vector, and we have an extra vector length right here. It's right there. So we don't need any of this stuff. That is a fixed point function. It's not a Newton iteration. It is a fixed point function. I can make it into a Newton. Fixed points are usually written with G. Go away. So I can make it into a Newton by saying 2L squared, squared plus L squared minus S. Now it's Newton. Now it's Newton. And then the analogy here would be if I wrote, let's just use this one. I'll just use the first one because it's the simplest one. Actually, x2 over x squared plus 1 minus x. So here we see we have a root at the same place where this guy has a fixed point. So we could do root finding on that. And maybe that's a way we need to approach this video. It now makes more sense. Hopefully it makes more sense now that I found the mistake. Not that my explanations were bad, but I do often have bad explanations. Thank you for sticking in there, sticking by me, and waiting out my mistakes. This is honestly the process that I go through in a lot of videos. I end up making mistakes in the math, and I have to redo the video. And fortunately, this time I caught it before I recorded it. Actually, a ton of mistakes have slipped into the videos as well, which is awesome. That sort of thing is just bound to happen, I suppose. Okay. So this is root finding, but this is kind of, I don't know, maybe it might be a good thing to mention, but I think we can start with this because this is a much simpler formula, and I can show its properties. I can say, well, Think about what happens when s, the length of s is equal to L, then this whole, then what's in the square brackets equals 1, so then the result of the function is just s. So s has a fixed point at L. And then when s gets bigger, the denominator gets bigger, and so the number gets smaller. And so that will contract it towards L. And when s gets smaller, the denominator gets smaller, the whole thing gets bigger, that will expand it towards L. Yeah, you should. You should always double check my equations because I'm a bad mathematician. A very bad mathematician. But I mean, that equation looked right, to my credit. Like, the problem wasn't that, like, it looked right in here. The problem was that I made an incorrect assumption. So you should check my equations and my assumptions. The bad assumptions are much more difficult to correct than the bad equations. That's just true about life in general. Okay. Good. So this finding this error makes everything a lot easier. I can just say, I'm going to present to you a formula that we can use to step us a little bit closer to the desired length we want. Why aren't we using this? Because we want to save on this square root right here. And if you look at if you watch my square root video, you'll see that we can just write s.s over here, s.s, and now we don't have to do the square root function. So this could be a little bit faster. And also it gives us the springiness. And so this is a fixed point. This is a fixed point. I wrote it up here. I don't need to write it again. And so this is called fixed point iteration. We're going to use fixed point iteration to find the to get the length of the section of Seaweed to approach our desired length L over many frames of the simulation. This would be a good point to explain contraction mapping. So that's a good question. Is this function a contraction mapping? Let's take a look. So it should be a contraction mapping in the neighborhood around where the fixed point is that we're looking for. And actually you can see that's true. Like if I take x to be a little bit less than 1 or a little bit bigger than 1, then the result's always going to be less than 1, but only a little bit less, right? Like the slope here is mostly level. So the output value doesn't really change much from 1. So I can just draw lines right here. Right here, you can see that the value didn't change much from 1. So the range is, you know, it sticks around 1 pretty good. So this function is a contraction mapping. And it's actually a pretty good contraction mapping. It will probably converge fairly quickly. And let's verify that. I'm gonna define a new function, g, and it's going to be, let's see. Let's just say the length of our seaweed should be 1. So I'm going to say x times 2 over x squared plus 1. And return that. So now I'm going to use an estimate of 0.9. Let's go hard on it. Let's use 0.5. And I see that it becomes 0.8. So the next estimate is 0.8. We feed it back into the function. Now it's 0.97. We feed it in there again, 0.999. So this guy is converging a lot faster than cosine was converging up there before. we already at this, so Python uses doubles. So Python is like, right, we talked about this in the first video, the difference in precision. Python has a lot more precision than we would have if we were just using regular floating points. And since we only have 7 or 8 digits of precision, we've basically gotten all of them with only 4 fixed point iterations. And we didn't have to use any square roots. So that's some cool stuff. So this guy is a contraction mapping. And fixed point iteration on him works. Let's do another dry run and see what happens. I guess I have to erase this too. Oh, I'm feeling a lot better about this guy now. Now that some dude talking to me. I should probably turn off Steam while I stream, huh? Now that we fixed this problem, I feel a lot better about explaining this thing. So let's give it a shot. Starting the timer. Here's the problem. We want to simulate some seaweed. And we're going to make the simplifying assumption that this is a simple indie game and everything is made out of blocks. And my seaweed is just a few lengths of green cylinders. And we want our green cylinders to be, ideally, length of L. They should all be length L. And then we're going to physically simulate them and let them float around in the water and let them, you know, try to float towards the surface even though they're anchored to the ground and all this good stuff. And I'm going to let S, the vector S, represent this vector right here that just goes along the length of the seaweed. Okay. Now, if I want to, so let's see, let me write these down. L is the ideal length of a section of seaweed, and S is a vector representing a single section of seaweed. So I could do this. I could say S and then multiply it by L over length of S. And that would get me a vector that goes in the direction of S but is exactly length L. That would get me what I want. But I'm not going to do that for 2 reasons. For one, I'm not going to do this. For one, I want to try and save on that square root. Square roots can be kind of expensive, and if we can avoid them, that's better. For two, I have another formula that will not get us an exact solution. It'll get us an approximate solution. And because it doesn't get us an exact solution, the seaweed will appear to be a little bit springy, which is good because seaweed is kind of a biological thing and it's, you know, it can stretch maybe a little bit. So maybe it's good that we use a sort of a springy simulation for it. So I'm going to write down a different formula right here. This formula is parameterized by L. That's what I mean when well, I don't know if I should use big words like parameterized by L. It has an L in it. Maybe I should just write this. Yeah, I'll just forget about that. Forget about the L. Why isn't it? What? What? This is the eraser. This is the pen. Weird. Okay. We're going to use this formula instead. Now this guy right here looks like it has the square root, which we're trying to avoid, but I can get rid of it by writing this as S dot S. So the dot product of a vector with itself is the length of that vector squared. So why does this work? Well, this function has an interesting property of when the vector s, I forgot to write, when the vector s is exactly length L, then f returns itself. Okay? So to show you that, I'm going to say assume that the length of s equals L. Then f of s is, okay, 2L squared over, now the length of s is L, so I'm just going to write L squared here. L squared plus L squared is equal to 2L squared, and so this is s. And this is called a fixed point. Specifically, when you have a function where the length, or the value of a function is equal to its input, this is the input and this is the output, and the input and output are the same, that's a fixed point in that function. And then I can draw a graph and I can say this is my function, okay, and this is boop, 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 boop. This is the fixed point right here, where this is the line y equals x, and this is the line g of x. I gotta remember to use g, because in the literature, g is what's usually used to represent fixed point functions. We'll write g right here. G. This is the point where g of x, this is the point right here where g of x equals x. And that's called a fixed point. And if certain conditions are true, then we can use a method called fixed point iteration to find exactly what that fixed point is. And we want to know that fixed point because that is the length of our, we need to use it to simulate this seaweed. So how does fixed point iteration work is probably the next thing that I need to talk about. We have this function g, okay, and we have an initial length of the seaweed, s naught. And then, so we're just going to pipe s naught through g, and we're going to get another value, s1. That's the first iteration. Now we're going to do the same thing. We take our result s1, we're going to pump it back through g, and we're going to get s2. And then we're going to keep doing this for as many times as we like. Eventually, if we keep doing this, we're going to get a more and more accurate representation of what that fixed point is. We're going to find closer and closer the value where g of s is equal to s exactly. But the constraint here is that we can only do this if g is a contraction mapping. Contraction mapping. And that means that, what does contraction mapping mean? Let's see. Which explanation of contraction mapping did I like the best? I think it was this one. If you have this range between A and B, where your fixed point is somewhere in the middle, okay, and you have A and B up here, A, B, then the value of g at A has to be up here above A. Here's GA. Has to be between A and B. And the value of, that's the value of g at A. And the value of g at B has to also be between A and B. So here's the value of g at B. All right. Between it, it can do anything it wants as long as it stays between A and B. If it does, it's a contraction mapping. And it has to be a contraction mapping in order for us to be able to use fixed point iteration. I think that's all I have to cover. So let's see what the timer looks like. 8 minutes. Oh man, just enough time for a quick code section. And if I can say all that stuff a little bit faster, this video might actually be under 10 minutes. Oh my God, it would be so great. So let me save this, export image, and where do I put it? Fixed points, save it, and open it, and put it over here as my cheat sheet while I record the video. Yeah, I can get rid of that. Oh, man. Okay. One thing left to do before we start recording this video, and that is do the code section. The code section. Let's open up the math project. Oh man, this is a situation where I feel like I can actually spend some time and implement these seaweeds in the game, and it would be a lot more impressive because, like, last time I couldn't because of the GLSL problem, but this time I really feel like I should. It's not a Newton. It's a fixed point. We'll do Newton next time. We will do Newton. I know Newton really well. I mean, it should be just as easy as, like, take this code, copy it in, but then I would have to fix that crash that I had. Quit. Control D. So let's see, math for game developers, and what was it? Run OS X, and what was this? Oh yeah, I better get rid of all this bisection stuff we did last time. Delete. Okay, and run it again, and we get a seg fault. All right. So let's do this. Debug OS X, and I have to type in my password. Crash. So let me see if I can figure out what the cause of this crash is. Oh, the renderer is null. That's interesting. Go to frame 4. Get renderer is null. Okay, I'm going to set a breakpoint at this line and rerun the program. Why does it keep stealing the focus? Oh, of course. The renderer is null. So print this. The renderer. Oh, come on. Okay, let me do this instead. Print this MP renderer. It is indeed null. Alright, well, is that my problem? Is the null renderer causing this problem? Where do I set the renderer? MP renderer. Line 128 of application.cpp. So let's set a breakpoint at application.cpp, line 128, run the program again. Oh, I didn't hit it. That's weird. Is there anywhere else I set it? That is for rendering context. So I set it here, but that's for rendering context. That's not what I want. Wait, is it? No, right now I'm in the main game loop. So that is weird. Let's go to this line. And it's in C application, open window. So let's put a breakpoint at the main function and go into open window. C application, open window. Oh, what is that? That's another breakpoint. Okay, delete that breakpoint. Relax, bud. All right. And that's weird. It failed to open the window. Let's just quit this thing and come back in. All right. I'm gonna actually tell it specifically be open window instead of be main. I'm gonna set that because there are apparently like 22 main functions, but there's only one open window function. All right, so stepping through the, why does it keep stealing my focus? Stepping through the window, open window function, and it still doesn't want to open the window. What? Oh, that would be why the renderer doesn't exist. Because the window's not opening. Alright, we can fix this. Well, let's not worry about the problem just yet, and instead worry about sending a proper signal when the thing doesn't open. Like it should. So I'm going to make this open window function return a Boolean and then say if it didn't open the window, couldn't open an OpenGL window. Oh my, return an error. And then there's one more thing I have to do. I have to go into, where's this function? No. Application.h, open window, make this into a bool. Okay, rebuild that. That still doesn't tell us though why the window failed to open. Now at least, you know, we get something reasonable when I try and run it. Couldn't open OpenGL window, so that's improvement. I should check pull requests on the Blue Ocean project. Did I get a pull request on it? Don't see any. No issues? We need a refresh. Don't see pull requests. Did you submit one? Okay. Why is it not opening a window? Let's see. I'm using GLFW. So GLFW open window. Let's look at the documentation. Okay, let's take a look now. Ah, thank you. Yes, merge that shit. Done. Thank you, sir. I didn't actually even look at it. Yep, okay, good. Do a fixed point iteration. Okay. Where was I? Looking at the documentation for GLFW. GLFW. Open GLFW. Open window. Open window. return values. If it fails, false is returned. Okay, that's good to know. Yeah. It doesn't tell me why it might fail, does it? Why is it failing? Why is it failing? Okay, maybe let's look through all of the options that I passed in. Maybe one of the options is causing the problem. So init didn't fail. And it stole the focus again. We are not full screen. We're requesting OpenGL 3.0. We are requesting multi-sampling. Maybe multi-sampling is not supported. It shouldn't just die if there's no multi-sampling, but you never know. And there's nothing scary about this number of bits. It's pretty normal. Let's see what the width and height are. And 1000 by 564. That's pretty boring. No cause for alarm there. So I don't know, maybe it was the multi-sampling. Nope, still couldn't open it. That's weird. I know OpenGL 3 is supported on this system. Do I know that? I don't see why it wouldn't be. This is weird, bud. Yeah, no, I don't want to chase this right now. Well, let's try Google search. GLFW open window fails. Actually, this guy's config looks really similar to ours. Oh. That is probably what's going on. I am requesting like a bad combination of OpenGL stuff. So let's do this. No? I don't know. Seriously? Yeah, I don't think I want to bother with this right now. Okay, well. I can't even remember if I've done this on the Mac before. I mean, I guess I haven't, because if I had, this problem would have already been solved. I know I ported it to Linux, but I guess I just didn't port it to Mac. Could have sworn I've used GLFW on a Mac before, though. But I don't think I've ported this project to Mac, which is why we're running into these weird problems now, which are boring. Okay, I'm going to take a quick bio break and try and decide what I'm going to do here, because I want to do the coding section, which would actually have this involved, but I don't want to sit here and figure out what the problem is on stream, because it's kind of boring. It has nothing to do with math. But we've actually learned all the math and gone through like the video that I'm going to record at least twice by now. So that's good. We've at least made some progress. So I'm going to take that quick bio break. I'll be right back. This is just the code portion of the math. Come on. Oh. This is the math we're working on. I think actually what I'm going to do is not bother with that, with trying to fix that. I'm going to record the math part of the video, and then I'm going to just end the stream and fix the coding problem offline and then record the coding problem and upload the video that way, because I mean, unless you want to sit here and watch me figure out this stupid bug. The problem is, I'll assume that Simon, you just joined us. The problem is, it's not opening. The library I'm using to open a window is not opening the window, and I've not ported to this platform before ever, and so I don't know why it's doing that. Now I have to figure it out, and I really don't feel like doing that right now. So. Oh wait, not that far. Like it's the same parameters that I pass in on Windows and Linux, and they work fine there. But for some reason, it's not working here. Yeah, GLFW. Yeah, I mean, and it like I don't. Maybe there's an error function, like a. Maybe there's a way to get like an error string, like what did I do? Like, give me something. Really? Some kind of error handling, something, error reporting. Tell me when something went wrong. Tell me why the window didn't open. Tell me what was the problem. That looks interesting. Ugh. Really? No. No, I refuse to believe it. Oh, I refuse to believe it. Apple OpenGL support. This document must be old. So it's saying that OS X doesn't support OpenGL 3 and above. And I'm trying to get a 3.0 context. Honestly, I'm not sure libraries are that. Yeah, no, loading the library isn't the problem. I've already done that. So this is 6 years old, so yeah. Yeah, everybody supports 3.3 now. Okay, so that's just old. What version of GLFW is this? GLFW. Oh. I think yeah, so I included the GLFW with the words. I included a version of GLFW with the Math for Game Developers project so that people could so people don't have to download things separately. And that's 2.7. And what is this documentation for? 2.7. Of course. Of course. And what is the latest one? glfw.org. 3.1.2. Great. Let's see what the latest 2 line is. GLFW2. Oh. GitHub doesn't even have version 2. Download download the old version. Version history. Okay, 2.7. So 2.7.9 exists. And it was released in 2013. So I don't want to update to 3.0. Try setting 3.2, delete profile and forward options. Really? Really? Where was I? Here. Try setting it to 3.2, delete the forward option, delete profile. What do you mean by profile? All right. Where'd you find that? That's a window. Well, wait, I don't see a window. Oh, yeah. Well, anyway, something happened. That's progress. Learn OpenGL.com. Okay. By profile, he means setting, getting rid of, oh yeah, the core. Yeah. All right, so normally when I'm running from the debugger, I press run, and it opens a window. This is what it does. It like, I'm gonna, no hands. It switches me over there and it opens the window. But now it's immediately closing again. So anyway, this is progress. Let's see what's going on. It's not giving me any message. So let's run it again. Stole my focus again for some reason. Thank you a lot, guys. That got me to the next step, so I appreciate that. Screen width, screen height. And this is just setting the position of the window, which is, yeah, there it is. It's kind of messed up, so you can't see it, but if I do this, maybe you can see it. There's the window. So there's something there. Set a bunch of, yeah, okay, thank you. Set a bunch of callbacks. Set the swap interval, set time, enable mouse cursor. Init glue, that worked fine. Oh. What just happened? Yeah, it stopped seg faulting. Huh? It's not even running anymore? What? Hold on, okay, let me delete all the breakpoints. Delete all the breakpoints, and then set a breakpoint at 126, because that's the last line that happened before things went weird. So we're not at 126. That's fine. So we're creating the renderer. Is our hardware... Oh. Okay, one more time. We're creating the renderer. We're stepping into some magic code that happens. Step into the magic code. So, little C++ for you. CRenderer is a class that must have some junk in it that has to be automatically initialized by the compiler. Where does it do that? This is why, like, I don't use C++ anymore, and neither do people like Casey Murtori, because it is, who knows what, like, I just pressed S like 20 times and it's not even, like, it's not, I can't tell what it's doing. C renderer, C renderer dot H. So I have to go look into the renderer class and figure out what objects it's trying to instantiate that are crashing. I wrote this code like 4 years ago before before Casey enlightened the world. So it's just making a bunch of vectors and floats and some bools. It shouldn't really be crashing. Another vector. 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 Another. Oh, okay. So it wasn't any of that. We got to the first line of the constructor. Let's step. I'll bet this is it. Is hardware supported? So that's supported. So at this point, we're compiling a test shader. We're going to see if it works. And did I get valid? Yeah, okay, I got valid object. So I think 0 is the invalid object. It could be -1 is the invalid object. But anyway, these are all 1, 2, 3. They're positive numbers. So I got valid objects back. And now we're going to compile it. I'll bet you that there's going to be some problem here. And it didn't compile, and it didn't link. All right. Well, let's go look at that code. 259. 259 in renderer.cpp 259. This at least we can get an error string for. Figure out why it's not doing what we want it to do. Get error. You can see I've been to this page before. It was a light blue instead of dark blue. That means I've clicked that button before. Okay, yeah. So this just gets a alright, well, that's better than nothing. So here's what we're going to do. We're going to say GL enum error e. I think error is like a reserved keyword, so I don't want to use it. I'll just use e equals GL get error. So this will get the error that occurred in the previous line. Like whatever this did that made it not work, it will return us that error right there. Yeah, pointless. It's very simple stuff. Like ideally you would have more structure to the code and it would automatically find errors for you. It would be more robust. But yeah, we're not doing that. Maybe that's why we're having these problems, because we didn't do it. But I can delete this breakpoint now. All right, so what error does it say? Oh, 0. Oh, that's good. Oh, wonderful. GL get error is 0. What? What? Did I do that right? Shouldn't be 0. No error was recorded. But you know what I probably have to do? You know what I have to do? So you call it once to reset it, and then you call it again to get the actual value. I'm thinking that is what's going on. So now it's reset. So now the error will occur. iVertex compiled is 0, so it did not compile. Now I call GL get error, and it's still 0. Let's look at GL get shader IV. Oh. Oh, this just gets the... No, it's not a stack. It's just every time you call a GL function, this is what I did wrong. Every time you call a GL function, it overwrites the an internal error buffer that it has. And so when you call GL error, you get the error from the previous function. And I'm not paying attention because GL get error IV is just it just gets a value. So of course it would never error if all it does is it gets a value that's trivial. The commands that actually generate the error are, here they are, GL shader source, and probably GL compile shader is the one that's gonna actually generate the error. So that's what I need to actually look at. And that's on line 238, oops. Where is my breakpoint? Line 239, okay, so delete that. Breakpoint at line 238, run it again. It ran to completion. Why would it do that? Breakpoint at render line .cpp line 238. Okay. So now, run compile shader, get the error. It's still 0. What? What? I'm sorry, guys. I should have done this a long time ago. I'm just trying to compile a shader here. This should not be hard. GL compile shader. Yes, it's exactly like get last error, except it's the OpenGL version. So yeah, this is OpenGL, not get last error, not Windows. So it's a different function, but it's analogous. This is how I get errors from shaders. Okay, let's try that. I'm kind of bad at the internals of OpenGL. I don't have everything memorized like Casey does. So I'm not a rendering programmer. So let's try that. Well, that did it. Great. Thank you again. Version 1.3.0 is not supported. Maybe it's because I got a 3.2 context. And I'm trying to use version 1.3.0. Yeah. So yeah, 1.3.0 is the shader version. let's do this. I think you're right. So this means bumping up the required version of 3.3 for everybody who uses that, but since it's so widely supported everywhere now, 3.3 is probably, I don't know, if you don't, let's see. I'm not sure if Valve actually tracks this. What, oh, I don't care. What version you need? Oh my god. Steam hardware survey. Don't install Flash. Don't want Flash. Okay. Yeah, I guess it doesn't look like they track OpenGL. Yeah, but probably 3.3, everyone's going to have it. I mean, we saw in this thing 3.3 across the board. I just don't want like somebody who has too old of a computer to not be able to run the sample code. That would kind of suck. But Mac is behind everybody else, and Mac supports 3.3 everywhere, so I guess it's reasonable to say. Oh, well, it supports it in 10.9. What am I running? 10.11. So 10.9 is fairly old. Let's see 10.7. 10.7 goes up to 3.2, yeah. All right. Well, let's just do it so we can move on. Oh, good. Yeah, that's true. They may not have the wherewithal and the knowledge to do that, to change it themselves. But now it won't even open the window again. So I guess I'll do 3.2 and then, god damn it, what was the shader version associated with 3.2? Was it 1.4? I don't even remember. It was 1.5. Okay, we'll try that. It worked. Wait, did it work? It worked. It worked. Alright. Init bunny. The bunny does. I can't believe the bunny's still there. Yeah, there he is. Where's the bunny? Stanford bunny.h. Where is he? Where is he? Include? No. Comment? Content? Where's the bunny? Yeah, that's the bunny. That's the bunny. This. All right. So I hard coded the bunny into the. I think I even wrote a script that outputted all of these. I don't know. No, it looks like I got this from Apple. Never mind. Yeah, but all the vertices for the bunny are hard coded into this source file, so that I don't have to distribute any like. First of all, you don't have to distribute any like supporting files that have to be loaded, and then the other thing is You don't have to write any loading code. Just put all the vertices right there in the source file. It's great. Anyway, so that works. The bunny. So we got a renderer. Let's just run it. And nothing shows. Nothing renders. Oh my god. Really? That's weird. Whoa. It's like stuck in a map lookup? No. Oh, I see. Okay, so why is it not rendering? Why is it not rendering? Yeah. Is it just frozen? No. So this is the worst kind of bug. Like, if it's rendering something wrong, then you can just hook yourself into the code where it's rendering wrong and fix it. If it's not rendering anything, then why? Like, you don't know. You have to go figure out why it's not rendering anything. So this will take some digging, I guess. Like, it could be the projection matrix isn't set up right. It could be our shaders are wrong. I could be using deprecated functionality. I don't think so. Deprecated functionality. Let's see. That's a good thing to check. And let me see if I can step into some code where I actually render something. Here we go. Begin render tri-fan. Okay, so it's actually building. When I render this triangle fan, it looks like it's actually building a like, it's not actually calling. It looks like it's calling old deprecated OpenGL fixed function stuff, but it's not. It's just storing it away, and then over here at the bottom where it says end render, it's actually gonna use program. Oh, that's it. That's probably it. Hold on, I just found it. Okay, remove this breakpoint. So, use program. Okay, so what just happened? Yeah. Yes. I'm not doing GL vertex. I'm doing draw elements or draw arrays or whatever. But I used a fixed function. Yeah, type. Yes, I used a fixed function type wrapper. Because it's easier to think about fixed function. And that's why Casey did fixed function in his first OpenGL video, because it's easiest, just easiest to explain. But you know, so like when you're trying to draw something that's like a ground, you can just write some code that puts each vertex in there instead of making an array and then bothering with. It's just easier to set up. I don't know. But underneath it uses the. Okay, so what just happened was, it said if not MP shader return, and it returns. So MP shader doesn't exist. So for some reason, the shader is not getting loaded properly. So this is the operative line of code right here. PSC program is wrong. Well, no, PSC program is right. It's model, and this is the model shader. So where are our shaders? Game? No. The shaders are content? Shaders. So here's the model shader. It's good. Well, I don't know if it's good, but it's there. So let's see, we have to walk into this get shader and see why it's not getting that shader. Here's some C++ junk. Did it find the shader? No, it didn't find the shader. So the shader's not even getting loaded. All right. That is a clue. Let's go to the shader library and figure out where it adds this shader. And shader. Yeah. I guess one question is, are any of the shaders not compiling correctly? So let's see that. If not, then print F. Shader, the name of the shader, did not compile. And I guess we're gonna do, this is so ugly, man. That's true. That was the first problem. I fixed it by making it 3.2. I guess maybe my computer doesn't support 3.3 or something like that. I don't know. So what is this? MA shaders. Let's open the shaders.h and see. Shader library. Shaders is a vector of C shader. So I'm now looking at a C shader. So then it should have a name. So I can write .msname.c string. So this will tell us if any of our shaders didn't compile. Oh wait. I put that in the wrong place. This is to recompile the shaders at runtime. It's already compiled, we're recompiling it. Let's put it here instead. If not compiled, print that. And then and equals compiled. And let's run it again. No, it doesn't look like we hit any of that. Looks like it worked fine. All the shaders compiled. Really? I don't believe it. I'm going to set a breakpoint at line 202. Breakpoint. Shaders.cpp line 202. Yes, it's all a huge hack. Trust me, my engineering does not look like this for like an actual project, okay? See, I didn't even get to line 202. So this is just like the toy project that I use to write math for game developers, so, you know, no judgments. No judgments here. 178. Let's put a breakpoint at 178. Does that get called? That does get called. And this is empty. Yep. There are no shaders. So this list is empty. Why is the list empty? That's our next problem. Where's the list filled? Here. So add shader is not getting called. Well, let's make sure add shader is not getting called. So we'll put a breakpoint at line 88 and see if that ever happens. No. So where does add shader get called? Probably from render. Yeah, load shaders. We're digging down to the heart of things here. I will bet you the problem is that this list directory function is not behaving properly. It's not giving me the proper list of shaders. So we'll set a breakpoint at line 76. No, wait, that was render.cpp, line 76. Render. Actually, let's clear away all these old breakpoints. So we just have the one. Okay, and AS shaders is, I can't read that. It's empty. So AS shaders, size equals 0, it's empty. So the list directory thing is not working. So let's see, platform. Well, that's good, because that means it's not an OpenGL problem. It's just a Mac supporting code problem. That should be easier to figure out. Oh, the dog scared you? Oh, sorry. Yeah, he's a scary sounding dog. The good news is that my apartment has never been burgled because he's very scary sounding. Okay. So we do opendir and that returns null. So what does S directory have? S directory. Oh, this junk is impossible to read. Another reason I stopped using C++. S directory is shaders. It's probably just running from the wrong directory. I'll bet you that's all it is. Opendir is not returning a valid directory, so it can't find the shaders directory. See, this is the kind of crazy stuff that you see in C++ programs that I can't believe I wrote for so long. S directory is a string. The only thing we do with it is we say .cstring, get the C string. So it doesn't need to exist as a C++ string. It can just be a const char. It can just be a char for all I care. When I say char, I mean char. And no, they don't use colons. They use slashes. Look, ls content /shaders. You know, the directory is /. It's just Unix. I think maybe an OS 9. Yeah, that's the old Macs. Exactly. Opendir is not invalid. Wait, there's a man. So there's a C function that I'm pretty sure returns the current working directory. So C current directory. Let's find out what it is and call it and see. Oh, I see I've done this before. Get CWD. Man, get CWD. I was close. There it is. So, oh great, I have to pass it a buffer? Lame. Yep, Hungarian notation. I don't use it anymore, but it still exists. Actually, I just got a new job, and there's Hungarian notation all over the place. And there's like the new code where they've learned that Hungarian notation is pointless, and they're not using it anymore. And then there's the old code, which has Hungarian all over the place. So it's just, it's never going to go away. It's never going to die. Get CWD. And we'll printf that. And we'll do it this way. Current working directory is this. And run it. Yeah, so it's running from the wrong directory. It should be in content when it runs. Really? Why is it in content? I say cd content. And it's not. It doesn't do it. It doesn't pick that up. All of these scripts that make it run, that like these OSX scripts, make me think that maybe I actually did port this to OSX at some point. Or maybe I only halfway ported it to OSX. I don't know. This is really weird. I have no idea what's going on. Let's try this. Oh, that's good. Oh, it's because I also need this. Copy lib GLFW here. All right. Shader model did not compile. Okay, that is different. That is a different error message than before. How am I going to deal with this? Oops. Yeah. So it looks like that same thing works in Linux, but it doesn't work. Okay, so copying the binaries up into the content directory works, but doing this thing where I cd into the content directory and then running the binary from where it currently is doesn't work. So at least we know how to fix this problem. I could solve it this way. I could solve it this way. Is that what I want to do? So we know this problem. We can delete that. I don't really think that's what I want to do. Here's what I'm going to do. I'm going to change this script to, where my script? This script, okay. Yeah, content, and copy mfgd content. cd content dot / mfgd. So I'm just going to copy everything into content and then run it from there. Because I want to be done with this problem and back to the math. This isn't really the best way to do it because since I have to copy MFGD, then I have to, so for Max, you need to use the entire directory. I don't know, man. I don't know what Max wants you to do. Like, ideally, the binaries would be here and the content would be there. And because the binaries are all platform specific, you don't want to mix them up with the content, which is generally like all content runs on, the content runs on all platforms. So you don't want to mix them up because the binaries are platform specific. And then that makes it easier for you to just say, you know, give me all the content and then only these binaries. But in this case, like, I'm just whatever. Since I copied the binaries, that means if I change something, it won't automatically find that binary. You know what I'll do? Change my mind about this and about this. Okay. I'm going to use ln. Which creates a symbolic link. So ln dash s, and I always get it mixed around. So let's see. MFGD. Oh, did I get it right? I think I did. Okay. Okay. Yeah, that looks like it worked. Yeah, that worked. Okay. Oh, does it really? I swear, man. I swear. So, like, Linux doesn't do that, though, because... Whatever, I don't even care. So, why didn't the shaders compile? What did you say? It's using an old version? You're probably right. That's exactly what's going on. So content, shaders, header. There it is. What is it, 5 now? I don't even have to rebuild. Debug. Run. Well, that's progress, I guess. Let's see if we're still having the shader problem. That would be a good first step. Yes, we are. So they actually compile now, but add shader. So let's put our breakpoint back here, render 76. So shaders, no, shaders is still size 0. Oh, I still have the same problem as before. Oh, come on. Oh, I know why. I'm being silly. I'm just being silly. Okay. That will fix it. Or not. Okay. Do we get a list of shaders? Good, now we have a list of shaders. Okay. Oh, I'm so happy. Do I sound happy? I'm super happy. So we read the shader. We get some data from them. Yeah, that worked. We push them back onto shaders. Okay. That all worked fine. So now it comes time to compile the shaders. And we get the shader header. What's that look like? That looks normal. We use multi-sample textures. Print F. Okay, so we found that file, which was the vertex shader file. We add a bunch of uniforms to it. We start reading the file line by line. We skip that part, 327. We close that file. Okay, we do the same thing with the fragment shader file. Create the shader, compile the shader. It compiled. It compiled. Oh yeah. So this is something that if I rewrote it today, I would do it completely differently. This is kind of a hack, but it shouldn't affect anything, I don't think. Yeah. Not even gonna bother explaining that. So that worked, that worked. Everything looked like it worked. We gather a bunch of data from all the uniforms. Okay. $448. Skip that part. In fact, skip this whole function. It looks like it's all working fine. So all of the shaders compile. That's fine. So let's go back to the rendering function and see if that is doing what we want it to do now. Okay. And I looks like it's not invalid. So we do return an actual shader. MP shader is not null. Okay, well we've beat that hurdle anyway. Really? Just debugging stuff is interesting? No math involved at all? Well, I'm glad. I'm glad it's not boring. Who knew programming could be so exciting? Okay, what was that uniform? So we're setting the projection view and transformations matrices, and that looks like a normal projection matrix. That looks like a good old regular view matrix. Yeah. Yeah, and that looks like, yeah, that's an empty transformation matrix. So all that looks fine. And here we go. Here's all this stuff we were talking about before. There are no textures on this thing. There's a normal map? What has a normal map? And oh, it must be that thing on. Oh, I know it has a normal map. Position attribute. Of course, everything has that. Here's draw arrays. Print s. So just 4 vertices. Yeah, so this is the ground, and one in video I made the ground have a normal map. So it draws that. And then it goes and disables everything for no reason. So good. So that all looked fine. I don't know about this. But nothing is rendering. Where's my render? Oh, it's the rendering context. Here we go. Rendering context. Rendering context. 299. Yeah. I'm gonna drastically change this value and just to make sure that it is having an effect, because I think the background that's displaying is this clear color right here. So I don't know, make this 0 or something. I'm pretty sure it's fine, but yeah, that's a different color. So only the clear color is getting through. That's good. Well, let's see what else could be going wrong. Shaders are working. Shaders are working fine. Oh. Oh, damn it. Thank you. Thank you. Yeah, I was talking about at the beginning of the stream that I want to do something more with that, but I haven't figured it out yet. Does that come standard on Apple, the profiler? Let's see. GL profiler from Apple. I'm surprised that Apple cares this much about OpenGL. Oh, my Apple ID? I don't know my Apple ID. Why do I need an Apple ID? What's my Apple ID? Maybe I can get it through the App Store. What's my Apple ID? Yeah, Simon, exactly. Exactly. We were going to do that. We were thinking about doing that at the beginning of the stream, but we decided to just do math instead. Okay. Here's a guess. Here's another guess. Ooh, that was a good guess. Okay, yes, I signed my life away. Did it download me something? Oh, see, I don't even have Xcode installed though. So this might not work. Fine. So now I have to restart it. Okay. Open. Attach to, oh, you know what? I should probably okay, now it's actually running. Come on. It's stolen my mouse. There we go. No, that's not what I want. How do I use you? Maybe we can have it launch it. You know what? I should probably do this thing where you drag it into applications to install it. Is that how you do it? Oh, I'm so bad at computers. Okay, open. It still doesn't want to let me attach to anything. I'll just have it launch it. Where's this thing? No, here, and here, and here. Wait. This one. Choose. Yes. Wait. All right. Launch. Yeah. And now what? This is pretty cool, but I don't know what it's supposed to do. Suspend it. Front buffer's empty. Good. Oh, defense system is my BOFS talk. If you want to see it, I still have it lying around my computer, but I'm not the one who actually gave it, but me and someone else wrote it together, and then she delivered it, and it's this one. Where is it? It's one of these. It's the it's the baseball guy. Here we go. Yeah. Yeah. Hour 16. So if you want to see my comedy science talk, this is where you go. 1 hour and 16 into the BOFS Seattle show. It's really good. We had fun writing it. Anyway. Under breakpoints I can see errors. Okay. Let's get it running again. Where's the... Too many windows. Resume. Oh, nice. Okay, there's the trace. Break on OpenGL error. Okay. Wow, this is cool. And you can set whether or not it executes, maybe? No? I'm getting a lot of errors, huh? Okay, let's do this. Well, I don't know. It seems like it's erroring for every call. And that's no bueno. Actually, that's probably the important call. Get uniform location And set uniform are erroring. That's probably my problem right there. All right. All right, that's good. That's good. Wow, that gave us some good information. Okay. What uniform is it trying to get? Is it gonna tell me? Yeah. Ooh. Yeah. That tell me the address, but the address of the string, but it's not, I don't see where it tells me the value of that string, which is really the information that I need. Well, really, I think it's probably barfing on all of them. Yeah. Well, there are only two. It's barfing on all two. This is super cool. So GL get uniform location. GL get uniform location. All right, calm down, bud. He just sees people walking past the window and he... Yeah, so what I think I want to do is stop this, quit, and then relaunch it here. And let's see, where am I calling get uniform location so that I can actually see what value it's getting. And I'll try here. Move my headers over to the right. Get unit. No, not at all. Oh, it's probably in here. Get uniform location. Here we go. Oh, that's a lot. But they're all called set uniform. So I'll set a breakpoint at set uniform. 7 locations. Run it. And nothing happens. It returns 6. Huh, that's not an error. That's also not an error. That's also not an error. So none of these are failing. That's weird. Oh, wait. Remember, it was fail. Oh, it's not saying anymore. It was only failing at get uniform uniform? Not get uniform, but just uniform IV. Uniform IV. I think. I don't remember. Let's try and rerun it. Launch. Okay. Get uniform 3FV. That's one that is crashing. So let's see. Get uniform 3FV. So this one, 514. No. How to get the same error from here to show up over there. I just want to know the name of the uniform. Maybe it gives me a line number? It does give me a line number. Oh my goodness, 502. Calm down, bud. None of these are failing either. You know what I'm going to do? Let it run for a while. Now it's running. Now I'll come back. Break at, what is it? Rendering context line 502. Yeah. Oops. Oh, of course. Of course. This is what I need to do. T-assert. Oh, great. T-assert. Okay, so I added an assert that should trigger if it's an invalid uniform. Let's take a look at it now. Remove all the breakpoints. And what? 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 Oh, I don't understand. I don't understand. So this guy is saying that there's an error when this guy is saying there's no error. All the uniforms have a value above 0. If I could get it to attach, what was that message that it was saying before that it couldn't attach until I did something or other? I thought I did that something or other, but I guess not. Restart it. Go to attach. Still can't attach. Okay. Please let go of my mouse cursor. Okay. Attach. Oh, there we go. Attach. Good. Now, trace. Breakpoints? Break on OpenGL error. Bam! What is this? What is this? Swap buffers is apparently having an error. That's no good. Enable vertex attrib array is having an error. Enable vertex attrib pointer is having an error. There's a lot of errors. Enable vertex attrib array is having an error. GL invalid operation. Yeah. So let's look it up. Docs.gl. Enable vertex attrib array. Yeah, that's not surprising. Invalid operation, invalid value. It's not there. That's not surprising at all. So this is not the first time where the error listed, the error that it gives me is not actually in the documentation. So thanks. I was really happy to see Casey use it. Somebody actually suggested it to him, and not only that, but he used it for the exact purpose that I made it for, which was, well, one purpose that I made it for, which was to like differentiate which functions, which OpenGL commands are available in different versions, which I don't know. I don't have them memorized. And it's really difficult to get information like, is this command available in this version? I don't know, but I need to know. But there's no way to get it, so seeing Casey actually use the stream to show that was really cool. See, I'm not even sure that this... Well, yeah, it would. So if all of these are returning invalid operations, then that would make it draw nothing. It needs to be able to do all this stuff in order to do what it does. And let's see, if we continue... Come on, continue. It's pretty useless, yeah. It's frozen? This is frozen? Hello? Hello? Boop, 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 boop. Okay, well, that's good. The debugger died. Glue? Like, did Glue have any errors loading? I don't think so. Let's do it this way. Let's do it this way. We're gonna set the breakpoint. We're gonna set the, we're gonna start it here at the very beginning of the debugger. Open up the profiler. Attach it now. Attach it now. Oh, it hasn't actually created the window yet, so I can't do that. Let's have it create the window. Okay, there's the window. And now immediately attach the debugger and then press play over here. Oh, I forgot to, oh, damn it. This won't work. This is not, I forgot something. Delete all those breakpoints. Open the window. Open the window. Go to the debugger. Yes, thank you. Attach to this. Okay. Attach. Okay. I broke it. Restart it. Attach. Now. Oh. Great. See, I want to attach before glue and it comes up. But it might not let me actually attach if I'm not running. Damn it. Damn it! Alright. Attach. I still can't attach. What is going on here? Oh. There we go. Just needed the good old reboot. Breakpoints. Break. That's weird. This thing is having errors all over the place. Maybe there's a GL extension version problem. I'm not using any extensions, I don't think. And I think if glue didn't come in, then the whole thing would have crashed. Because if glue doesn't come in, it doesn't get the right pointers to all these functions. And then it just doesn't. And then it just crashes when you try and call any of the functions, so I don't think that's the problem. Use program 3, it says that's an invalid enum. 3 doesn't look invalid to me. 3 is just, 3 is not like -1 or anything. 496. So now I have it loaded in both debuggers at once. This is super weird. And program 3. Program looks fine, man. Program looks fine. But it says it's an invalid enum. GL use program. Go. It's not here. I don't understand how use program cannot like the program that it got passed, because I wouldn't have gotten the program number, but like 3. I wouldn't gotten 3. I got directly from OpenGL. I don't know. I got it from OpenGL. I passed it right back in OpenGL. Like, I think we just looked at that code where it gets built, where this value gets assigned. We were just looking at it before when it compiles the model. If they weren't linking right, I wouldn't have gotten this 3 back. See what else it's got for me. Oh, did I just freeze it up? Yes. Oh. There we go. Got both of these debuggers chugging away at it. Alright, so this is a bunch of junk. GL use program 3. This is what failed. Oh, wow. And then enable vertex attrib array 5. This guy also fails. Invalid operation. Oops. Maybe it's invalid because it's not supported. Oh, look at this. GL version 4.1. I don't understand OpenGL, dude. If it has 4.1, then why was it balking at 3.3? We had to switch it back to 3.2 for it to work. I don't know. I don't know what's going on. So this is invalid. It doesn't like this 5. Well, it doesn't say it doesn't like the 5. It just says invalid operation. Where's this call? 782. 782. Yeah. No other errors. Just this junk. See, then now it's what? Steve Jobs ghost. This is giving invalid operation on not even a negative. I'm not even passing a -1 into GL uniform. I'm passing a valid uniform. Maybe there's a OpenGL command that tells me if my object is valid or something. Validate program pipeline. I don't know why I'm using that search when I can use this search. Validate is enabled, is list, is program. Is program? I guess. Let me see. What's it saying it's not? Is uniform. Is uniform is not here. Okay, well, what else are you balking on? Is vertex attrib array? It's not going to have that. Oh, is vertex array. No, that's not what I want. Bind vertex array. Yeah, that's different. That's a vertex array, not a vertex attrib array. Those are different things. So let's continue. Vertex attrib pointer. Okay. Oh, draw arrays had an error too. That's great. Okay. Now back to all these again. Wonderful. Flush has an error? How can flush have an error? Oh, because swap buffers. Swap buffers has an error. I don't get it. Yeah. You're probably right. I need to update to the newer GLFW, which I don't want to do. All right. I'm not going to do that right now. I am going to do it, but right now I just want to finish the rest of this video. Finish the rest of the math section anyway. So I think I think you guys are right, and I need to update to GLFW 3. Glue should be fine. I can't imagine Glue is doing anything wrong. It's got to be GLFW, specifically because 2.7 doesn't support Mac. He wrote that in his documentation. So yeah, I think you guys are right. So thanks a lot for that recommendation of the software. I'm going to look in this graphics tools library. It looks like there's some, look at this, a shader builder. I don't know what this is, but it looks interesting. This, oh, that looks useless, but some of this stuff looks really cool, so I'm going to check that out some more later. Not going to worry about this for now. Gonna do this. Gonna record this video. Put my cheat sheet over there. 2 minutes, and then I'll record this video. 2 minutes. I'll be right back. I'll be right back. Take some water and stuff, you know. At least we got the math right. Oh my god. Mischief is so pretty. Look how pretty it is. Alright, what are we doing here? Close that. No, don't save. Camtasia. What is this? No. Don't care. Start recording. Microphone check. It works. So let's give it a shot. No, wait, no. Not the whole screen. Start over. So far, so good, guys. Please don't do that. Why is it doing that? Oh, come on. I don't know if the region is in the right place because every time I go to set the region, it does this. Why is it doing that? Okay, it looks fine. Yeah. Lights, camera, pretty lines. Welcome back to Math for Game Developers, where today we're going to do fixed point iteration. Let me not start it that way. Start over. Start over. Off to a bad start. Start over. All right, where were we? Welcome to Math for Game Developers, where this week we're going to take the problem of physically simulating a few links in a chain of seaweed. Seaweed. Pretend that our seaweed gets modeled by each link being a certain length, L. This is a very simple game, so it's not supposed to be photorealistic or anything. We just kind of want it to resemble seaweed, and so we're going to have each length here be L, and then we're going to physically simulate it so it looks like it's flowing around in the water. And so let's just look at the simulation for an individual segment of this seaweed that I'll call S. And so let's see, what are our variables here? L, that is the ideal length that we want our seaweed segment to be. And S is a single segment. It's a vector that represents a single segment of seaweed. It's a vector that starts at the bottom of a segment and ends at the top of a segment. Now, we could do like this. We could do this formula right here. We have our length S, and we want it to be length L. We have our segment S, we want it to be length L, so we multiply by L and divide by the length of S. Okay, and then that will be the new length of the segment, to make sure that it's always our ideal length. But actually, we're not going to do that. We're going to take a slightly different approach. This approach would work. It would work fine, but we're going to learn something new today, and that will mean that we have to take a different approach. We're going to make a new function called g of s. All right? And I'm going to set it to be a special thing. So let me just write this, and then I'll explain what it means in a moment. 2l squared over length of s squared plus l squared. All right? So this is a special formula that will let us do physical simulation of this seaweed in a special way. So it has two advantages over the other formula. One is that it avoids the square root function. Here in the denominator we have the length of s, which, as you know, is calculated by using a square root. But here, this is also a length of s, but we can calculate it using s dot s, which is equal to length of s times cosine of 0, which is equal to length of s squared. So we avoid the square root operation which makes it a little bit faster. But it's not perfect. It's not perfect. It doesn't get us the length of s unless the length of s is already equal to L exactly. Let me rephrase that. It doesn't set the segment to be length L unless the segment is already exactly a length of L. And let me show you what I mean. Let's assume that, picking a new color, let's assume that S is already length L. Then this G function, okay, then, that's a little arrow. Oh, I'm bad at drawing arrows. Then this G function is going to look like this. The numerator stays the same, but in the denominator, we have length of S squared, but that is L squared plus L squared. And since what's inside these brackets is 2L squared over L squared plus L squared, that is all equal to 1. So this is equal to S. Okay? So when S is already, when the length of S is already equal to L, then this function gives us the right result. It gives us a vector of length L. But what happens when the length of S is less than L? Then, oh, that's a better arrow. Then G of S is equal to the same thing as before, except we'll put 2L squared in the numerator. But now the length of S is slightly less than L, so you'll have something a little bit smaller here in the denominator. A little bit smaller, which means this whole number will be a little bit bigger, which means that G of S is slightly bigger than S. And remember that the length of G of S is slightly bigger than the length of S. Okay? Which is good because we want we want S to be length L. And so if we run it through this function, it gets us slightly more there. And if we say that it's slightly bigger than L, then we're going to get the same thing, except the denominator is going to be slightly larger instead of slightly smaller. And so we're going to get a slightly smaller vector. Okay? So let me just phrase that again just so that we can understand what's going on here. If we have a vector that it's the size we want it to be, it is equal to the ideal length, then everything is fine. This function doesn't change anything. If it's slightly less long than the ideal length, then this function will increase it to approach the ideal length. And if it's slightly longer, then it will decrease it to approach the ideal length. And so I'm going to try and draw that in a picture so we can get a little bit better of an understanding here. Here's a graph. Okay. Here is the function. I'll do it in this color. Here's the function that it looks kind of something like this. And this is what happens. This is the line y equals x right here. And this is the function g of x. And you can see that these two lines have an intersection. Okay? When g of x is a little bit less than x, I should say g of s. When g of s is a little bit less than s, it pushes it this way. And when g of s is a little bit bigger than s, it pushes it that way. This has a name. It's called fixed point iteration. And when g of s is equal to x, it's called a fixed point. Any function when g of x is equal to x, that's called a fixed point. And it's useful in this case because it can help us simulate this seaweed. And our method of doing that, by just putting s into this function and getting a slightly better approximation out, that is what fixed point iteration does. And we've been doing it with this method. So fixed point iteration is pretty cool and useful. And there are a lot of situations where we can use it, but we have to know, like what is the situation where we can and what is the situation where we can't. And there is a condition that you have to satisfy in order to be able to use fixed point iteration. And that is that it has to be a contraction mapping. So what does that mean? What is a contraction mapping? So here's my function. Okay, I'm going to draw another graph here. Here's A, here's B, here's, this is not to scale, huh? Here's A, and B's like up here. Here's B. So I have my function. It's a I'm gonna draw my function here. It's a contraption mapping f. The value of my function, g of x, at A is between A and B. So this is g of A right here, and you can see it's between A and B, so it's fine. And this is g of B right here, so it's fine. And all of the values in between are also between A and B. If that condition is true, then this function is a contraction mapping. In other words, the range that you pass in, this is the range right here, gets squeezed. On the output, it doesn't take the whole range. It now only takes a subset of the range. And so when we do our fixed point iteration, our resulting values will get squeezed closer and closer and closer to the fixed point. That's why fixed point iteration works. So hopefully this will become more clear when we do the code section of the video, which we're going to go to now. And that's a lie. We're not going to go to it because I want to get some dinner, basically, is the reason. It's 5 o'clock. I've been doing this for 4 hours. I really appreciate you guys hanging around and watching me do this and helping me solve this problem, which I think I just need to, I just need to do GLFW 3.0 to fix. So, but we got half of a video, and Simon wasn't around for it, but we had a little bit of a misadventure, which was funny. When for the first like 2 takes, I got the math wrong, and I did like some horrible, awful things that that we had to discover the fix for. And oh my goodness, 10 minutes? I can never get this freaking size down to less than 10 minutes. Hopefully the code section won't take too long though. So anyway, once I do this, I'm gonna eat some dinner, and then I'm gonna do the code section. Thank you very much. Once I do this, it will probably be organizing my thoughts here. So once I do this, I'll be like 2 videos ahead. So next week, I don't know if I'm gonna do another, like, as far as I'm ahead on videos, I might not stream. I might, if I feel like it, I might stream. But it will definitely be at the same time, 1 p.m. Pacific from now on, if I do stream. So yeah, and the video will be available, 4 hours of me spewing gibberish. So have fun of that. Thank you guys again for coming and hanging out, and signing off.